Understanding the math behind the BP base block's getAttached location function can further put into focus how vectors are used and provide an example of one way to use a static mesh's normal values. Our objectives for this module are to explain the coordinate system which our game is built on. We'll demonstrate how the getAttached location function uses a normal to figure out which direction a face is pointing. Finally, we'll solve the question of where to place a new block when an existing block is clicked on. Our game is built on a 3D Cartesian coordinate system, defined using an x, y, and z axis. To keep things simple, we've made the point of origin of the floor block snap to a grid of 100. In our system, x values increase in a positive direction moving forward, y values increase in a positive direction moving to the right, and z values increase in a positive direction moving up. All axes decrease in value in the opposite direction. Unreal units are 1 centimeter. Our blocks are 100 centimeter cubes. In other words, they are 1 meter cubed. We'll use these figures when we determine where blocks will go in the world. In the block game, all blocks have a point of origin in their lower left-hand corner. This is how we specify where to add a new block. We do this by providing the location of the bottom left corner of the new block in global space. Now that we know how the coordinate system is used in our game, the next piece of the puzzle is the normal. Normals on a static mesh define which direction a face is pointing. When we specify normals on the BP base block, we're indicating the values in the x, y, and z axis. Normals are normalized values, meaning they have a value between -1 and +1. If a normal's value is -1, it's pointing in the negative direction of the axis that it's specifying. If a normal's value is +1, it's pointing in the positive direction of the axis that it's specifying. If a normal's value is 0, it's perpendicular or on edge. We use a vector to specify the normal. By doing so, we can identify which face was clicked on, or more accurately, where the hit occurred with a line trace. In this version of the block game, I added some additional information to show where the point of origin of certain blocks are. For example, the floor block is showing its point of origin of x0, y0, and z0. On the block that was added, its point of origin is 100 in the x-axis, 100 in the y-axis, and since it's on top of this floor, it's at 100 in the z-axis. The normals on the faces are shown on this specialized block as well. On the face that we're looking at, it's facing in the x-axis in the negative direction. So its x value for the normal is -1, and it is 0 for the y and 0 for the z. On the opposite side of that block, notice that the x value is 1, and the y and the z are both still 0. On the y side, we've got an x of 0, a y of -1, since it's facing in the negative y-axis, and a z of 0. And on top of the block, we see that we've got an x and y of 0 and a z of +1. Observe when we place another block, we get the new coordinates shown on the block, and in the x-axis, we're at 300, here's 0, 100, 200, 300 in the x, 300 in the y, so there's 0 in the y, 100, 200, and 300, and we're still at 100 in the x since we're on top of this floor block. If we add a block on top of that, the x and the y stay the same, and the z goes up to 200. When we add one on top of that, we should see a z of 300. Back to the getAttachLocation function in the BP base block. This function receives two vectors as parameters: the location of where the crosshair was when the player clicked, and the normal, the direction the face that was clicked on was facing. Both of these parameters are vectors. This means that they both contain an x, y, and z value. As an example of how the function works, let's use the floor block at 100 in the x, 200 in the y, and 0 in the z, and work out what happens when a player clicks on top of that block at the location 153 in the x, 229 in the y, and 100 in the z. The cursor in the graphic on this slide approximates that location. The normal value will be 0, 0, 1 because the face that was clicked on is facing in the positive z direction. It's facing upwards. The first node adds the two vectors together, which sounds more complicated than it is. It's just straightforward addition. The x values are added, the y values are added, and the z values are added. In this case, the sum would be 153, 229, and 101. The next node subtracts 50 from the sum of the previous node. Again, it sounds more complicated than it is. This simply subtracts 50 from each of the three axes. The remainder of this subtraction would be 103, 179, and 51. The next node snaps the remainder of the subtraction to a 100-unit grid. This rounds down any axis that's 50.0 or below to the nearest 100 and rounds up any axis that's greater than 50.0 upwards to the nearest 100. The result of this is a vector snapped to a grid that is a vector that defines the attachment point for the next block. 103, 179, 51 would snap to 100, 200, 100. Once again, using a slightly modified version of the game, I've added a cursor that shows where the next block would be if you were to click. And you could see that the math is fairly straightforward. When we are at 0, 0, 0, and we put the cursor right on top of that block, the only axis that's going to change is the z-axis. We're going up one whole unit, or 1 meter, or 100 centimeters. And if we click and add that block, we'll get a block at x0, y0, z100. The math works no matter which side or which face we click on. And you could see that it's very fast and very accurate. To wrap things up, the math behind the getAttachLocation function is straightforward. It's addition and subtraction. Using vectors is also straightforward. Vectors are a structure with three values, an x, y, and z. Adding vectors and subtracting singular values from them involves applying the operation to each axis and obtaining the result. Having a good grasp on the 3D coordinate system and a concept such as normals can help you solve more complex problems in the future. In this module, we explain the coordinate system in which our game is built on. We applied the 3D Cartesian coordinates and surface normals as a means to determine which side of a block was clicked on. We determined where to place a new block when another block is clicked on.